So moving along with Faraday's Law chapter, we want to look at the EMF induced on a moving conductor. So even when a conductor is moving through a magnetic field, we are going to see a force on the charged particles within the conductor. So a charged particle that is moving perpendicular to a magnetic field with a speed v experiences a force. We saw this in our previous chapter, right? The force it experiences looks like this. So if our velocity and our magnetic field are perpendicular, as they are in our diagram here to the left, that cross product just becomes a simple multiplication. If they're not perpendicular, we just have to take into account the angle between the two things, V and B. Okay, so if we've got a rod that's conductive moving in a magnetic field, those free electrons in the rod move along with that rod, right? And each electron is going to feel a force that looks like F equals QV times B, right? So in this case, we could say that the force that each electron feels, and this is just the magnitude of the force. Remember, the direction is going to be based on the charge of the particle, and electrons are going to feel an opposite force as protons. That means electrons are going to be pushed downward in this case on the picture to the left. We know that the force that this electron feels, we could write as Q times E. So in this case, we could compare these two equations and get an induced electric field that is related to both the speed of this rod and the magnetic field that it is moving through. Now, if this is a constant magnetic field, we can talk about, and I'll put little hats on this V so that we know we're talking about a capital V. We can talk about the change in potential, remember, so our voltage, being related to that electric field over the length of this rod. So you can see there's an L labeling the length of this rod. So the difference in potential from the top end to the bottom end of this rod is going to be related to the magnetic field, the length, and how fast it is moving through this external magnetic field, right? So we can calculate the EMF, the work needed to move charge from one end of the rod to the other, the work needed to move a charge from one end of the rod to the other. We're just going to do force times distance. And in this case, that work is QVB, that's our force, times our distance, L. And then our EMF is the work that's done per unit charge. In this case, we just divide out that charge Q and we get VBL. So our EMF and our change in potential, we're going to get the same relationship there. That's good that our equations are consistent. So that's the EMF induced in a moving conductor. We get charges pushed to either end of this moving conductor because they are moving through a magnetic field. Now, we get that change in potential, but if we don't have a closed circuit, we're not going to have any current. So let's look at the next step where we do close that circuit and have a loop to see what current happens. So if we have EMF in a moving conductor where we have a closed loop like what's shown on the left here, we can say that we're going to use Faraday's law to talk about the induced EMF and the current because of the induced EMF. So here we have a rod that has some sort of applied force, and we are going to move it to the right at a speed v, which means that this distance x is increasing with v times time. So our x equals, say, maybe our initial x plus v times t, right? So our flux through this loop, I'm going to grab a different color, through this loop described here is going to change because the size of our loop is going to change. So our flux is going to be BL times X, but X is going to be changing and increasing. Okay, so when we go to figure out from Faraday's law the induced EMF, we're going to look at how our flux is changing in time, and we're going to get that from this over here. So B is not changing. It is constant throughout this area that we're talking about, but the size of our loop is changing. So DA is changing with time, and it is changing with time at a rate that is L times V. So we've got that negative sign letting us know that the EMF is in a direction that's going to oppose this change in flux. So that equation that I have right there, that our EMF is equal to BL times V, is valid as long, and let's write this in red, as our magnetic field is perpendicular to our length and perpendicular to our velocity. So that's something to watch for, to make sure that you can take your dot product in your flux and turn it into a simple multiplication for that EMF. So our motional EMF is an EMF induced on a conductor moving in a magnetic field. So motion is causing the EMF, so it's motional EMF. The current induced here in this case is gonna look like I equals our EMF divided by R, and we're just gonna take the absolute value because the negative sign is just gonna give us a direction. So that is just from Ohm's law. So our current induced in this case is B, the length of our conductor, right? So L is this length here. V, the velocity of our conductor, and divided by R, so the resistance of this loop of wire. And in this case, they say the resistance is all concentrated in this resistor. All right, so what about power? So our power, we could think of as our force applied over that constant velocity, or you could just use I squared R again. You could use all those equations. So the force applied is going to have to resist, right? For a constant velocity, it's going to have to be equal and opposite to this magnetic force. So it's going to have to resist that magnetic force times our velocity. So the power that we have to supply to get this thing moving looks like B squared, L squared, V squared over R. And that's just from me inserting this solution for what our current was. If we look at that a little harder, I've got my EMF squared over R, which is just one of our power equations that we have already used. Okay, so our EMF induced in a moving conductor, we can look at what happens when we go to a bigger area, like what was just in my previous example, or what happens when we go to a smaller area. So by Lenz's law, the induced current has to be in a direction to oppose the change. So if we are moving to the right, we are increasing the area, and we are giving ourselves more flux through our current loop. So if we're giving ourselves more flux, the direction of this magnetic field is into the screen or into the page as you're looking at it. If we're moving it so that there's more and more magnetic field, magnetic flux into the page, we're going to induce a current that is going to induce a magnetic field out of the page. So I can write out in a small letter, right? We want to induce a magnetic field out of the page. So if we use our right hand, we're going to point our thumb in the direction that we want the magnetic field, and our fingers are going to curl around in the direction of current. So in this case, that tells us current needs to go this direction, as it's already labeled in this image, right? That'll produce a magnetic field in that direction. So that magnetic field isn't enough to cancel out the change in in flux, but it is going to oppose the change. Okay, so if we go the other way, if we move our rod in towards our resistor, we're shrinking the area of our current loop. And what we're going to see if we're shrinking the loop is we're going to see less flux through the loop. And so our induced EMF is going to want to resist this. And so our induced EMF is going to be into the page. So our induced EMF is into the page. And again, if we use our right hand, we point our thumb in the direction that we want that magnetic field to happen. And our fingers will naturally curl around in the direction of the current that causes that magnetic field. So that's the direction of our current if we move the rod in. So moving this rod back and forth, you can induce current in back and forth directions, which is kind of interesting. So let's give ourselves an example of this problem. We want to look at a loop that's moving through a magnetic field. So we've got a rectangular loop that is, and they say metallic, but we know that means conductive. It has dimensions length and width as they're labeled in the picture there. It has a resistance R, and it's moving with a constant speed to the right. The loop passes through a uniform magnetic field directed into the page and extending a distance of 3 widths along the x-axis. Define x as the position of the right side of the loop, so as the right side of the loop, along the x-axis, and plot the magnetic flux through the area enclosed by the loop, then plot the induced motional EMF, then plot the external applied force necessary to counter the magnetic force and keep the velocity the same. Okay, so let's start with that first thing. So the magnetic flux through the area enclosed by the loop. So if we define x equals 0 as starting out with this right edge of the loop just outside of our magnetic field, there is no flux through the loop. And then it increases to some maximum value. The maximum value it increases to, if we're all perpendicular, is going to be just b times a. If we're not perpendicular, we'll have to take the dot product and again account for the angle between those two things. But so b times a, b is our magnetic field, so b is b. Our area of our loop is L times W, so the max is this BL times W. Then we cruise along within this magnetic field for a certain amount of time, and the magnetic field is constant, so we see no change in flux, right? Even though we're moving through the field. Then as we begin to exit the field, we see a nice steady decrease as our area that is covered by the magnetic field decreases back down to 0. So that's our magnetic flux through the area enclosed by the loop, right? So flux, remember, I'm going to draw it this way. If there's a region where only part of our loop is covered by our magnetic field, this is the only part that is contributing to the area of that flux, right? So that area that's covered by the magnetic field is the only area that's contributing to that flux. So that's where these up and down slopes come from. Okay, so part B asked us to plot the induced motional EMF in the loop as a function of x. So let's go back to this. We want to look not at just phi, but at d phi dt. So this first region from 0 to W, as we're entering this region of magnetic field, we have a linear increase. So d phi dt is positive, and it's some standard value, so some constant value, because that's a nice linear increase. So we'll just call it C. And then in this region where we are leaving the magnetic field, our flux looks like it is a downward slope, so it's a negative sign, and again, some constant value that has to do with our velocity and how much time it takes us to leave that area. Okay, in this region, that's a flat line, so there is no slope there, there's no slope here, there's no slope after 4W. So if we are looking at our motional EMF of the loop as a function of x, we are looking for negative our slope of the previous graph. So here we have some constant, right? And I did not write it out, but negative of our positive constant is that negative c. And like I said, we can relate that slope to how fast we're moving into and out of this region. So how fast we're moving is that velocity. So our induced EMF as we're moving into the region of the magnetic field is negative BLV, again in a direction to oppose the change in flux. And then as we move out of the region, that same constant, except now in the other direction, it's a positive BLV. And in that middle region, again, it is 0 because we had that flat line, that flat slope, no change. Okay, so part C says, let's plot the external applied force necessary to counter the magnetic force and keep our V constant as a function of X. So this is in your book on page 947 if you want to follow along there. But the external force that has to be applied to the loop to maintain the motion is 0 because before it enters the field, there's no magnetic force to work against. So it starts out as 0. And then as we're entering the field, to maintain a constant speed, we've got to be equal in magnitude and opposite direction of the magnetic force exerted on that side so that we're in equilibrium. So if we want constant velocity, what we want to do is have all our forces add up to 0. So this applied force has to counteract our magnetic force that our loop is feeling. And it's only going to feel that force again as we enter and exit the region of our magnetic field. All right, that's a good place to pause and pick up with the next video.